Dr. Chen, we can't hear you.
Can you do it now? All right.
Yeah.
Okay, so our job is try to do the next chapter, which is the last chapter of the semester, Laplace transform. Okay. To do Laplace transform is fairly easy because we only need a certain kind of properties of Laplace transform in order to solve differential equations. But I think this is such a rich topic, so that's why I said like we probably want to go from Fourier analysis and give you an intuition of why the transform looks this way. Okay. So to introduce the Laplace transform, we take L as the notation for Laplace transform. We take bracket instead of parentheses. Okay. So we transfer a function of t to be a function of s. And that is going to be this. Notice, you are taking the integration with respect to the function and the variable t. So when you finish, all the t will be gone. You have a starting and ending point. So finally, what you end up with is a function of this s here. Okay, you put in a different s, you receive a different number. That's basically what the Laplace transform is, which if this is the first time you have ever seen something like this, it looks pretty weird. Later, we will show this one has really nice property and it will help us to solve a lot of ODEs. But for now, I want to spend some time to talk about where the idea of Laplace transform come from, okay? And also to discuss a little bit about the relationship between Fourier analysis and the Laplace transform. So before we dive into the final chapter, I want to focus on this. Number one, because it will help us to understand the Laplace transform so much better. Number two is Fourier analysis. I think it's not exaggerating to say that it's basically the foundation for any kind of, I won't say any kind of, for most technologies you use on a daily basis, like a smartphone, anything that involves signal processing, you will have a heavy usage of Fourier analysis in there. And of course, as far as I know, we don't have any classes in UWL, in the mathematics department, to teach you about Fourier analysis, which is really sad. So I think it's worth the time to talk about it. I don't have much time to prepare for this lecture, so I did it as good as I can. This is the first time I'm teaching it. I'm trying to condense a lot of information into a very short period of time. So there may be some gaps between one thing goes to another. Maybe I made some assumption that you know something. Maybe I just didn't think it careful enough, okay, about what you will see this thing for the first time. So I would say for this part, since you cannot get it from the book, stop me anytime you have a question so we can have a deeper discussion. Okay, because I don't have experience of this by condensing so much information into just hopefully one lecture. Okay, so stop me anytime. Okay. So the first thing we want to talk about is something called inner product, which you have done before. It's basically something like this. You have a vector A, you have a vector B. Okay. Okay. And one type of inner product we are very familiar with is actually dot product. Okay, if I give you 1, 2, 3, and I give you 4, 5, 6. These are two things. I call it A and B. Then A dot B is nothing but B transpose times A, which is just 1 times 4 plus 2 times 5 plus 3 times 6 equaled whatever number you have there. Okay. Now, according to geometry, it's actually very easy to see. A dot B is nothing but the magnitude of A times the magnitude of B and times the cosine theta, where theta is the angle between these two vectors A and B. Okay, so this will actually give us a natural way to figure out how similar two vectors are. Moreover, when I say similar, I'm more talking about the direction. So you can have two vectors going like this and this. And if they're in the same direction, that basically means cosine theta is almost like 1. That means your theta is almost like 0, right? And if it's -1, that basically means, okay, means one vector goes this way, one vector goes this way. Okay? And if cosine theta equals 0, it basically means they're orthogonal to each other. Okay, so A dot B is already a very good indicator to tell you how similar two vectors are, okay, because it contains the information of cosine. Okay, now in statistics, this is basically what the definition of covariance of two vectors. Okay, and it's closely related to correlation of two variance. Because correlation, you basically, how to say, this is just the correlation, which is basically A dot B, but then you try to normalize everybody before you do it. So you just care about the direction. You don't care about how long each one is. Okay. So once you divide the length of A and length of B out, you only have cosine theta. Then this theta is going to tell you, are these two things pretty close to each other? Or are these two things very to the opposite to each other? Or are these two things kind of like orthogonal to each other, which means they're totally independent. They don't have any correlations. Whatever happens in X does not affect what happens in Y. Sounds good? All right. Now, we need to extend this thing a little bit. This time, we don't want to have vectors because vector has dimensions. You can have a 10-dimensional vector, 20-dimensional vector. But what if you have infinite dimension? That means you have a vector, but this vector has infinite length. What kind of thing is like that? Well, this time you want to tell if two functions are similar to each other. Or let's say you want to tell the correlation or covariance between two functions. On an interval AB. Okay, it's pretty easy to understand. If you have a function goes up here, goes down here, goes here, and horizontal here, and then goes down. You have another function, okay, which similarly goes up as this one goes up, goes down as this one goes down. Okay, maybe a little bit different here, but then you can see they're kind of similar in terms of the trend. That means if I rise, do you rise? If I drop, do you drop? If everything matches perfectly, we have a perfect correlation, which is 1. Okay, and we may have a perfect negative correlation. Wherever you go up, I go down. That will be a correlation of -1. Okay, or maybe we're just totally independent of each other. Good so far? Okay, so how do you tell if two functions are similar to each other? Again, you want to take the dot product, of course. But can you see that? This time your dot product cannot be just A1 times B1 plus A2 times B2 plus A3 times B3, because now you don't have A1, A2, A3 anymore. You have all the possible values between A and B for each function. It's not even a vector. So I want to extend this idea to a new idea which will contain the correlation between two functions. Let's use X instead. Sounds good? All right. How do we do it if you have two functions? You want to check the correlation between them. Well, number one, I don't know about continuous function. I do know for discrete values. So the first thing you can do is you can sample the points. You can sample the points here. You can sample the points here. You can sample the points here. We call them x0, x1, x2, all the way to xn, which is b. So you sample both functions. Let's sample n plus 1, n points. What did I do? I did n plus 1 points. Okay. N intervals. Okay. Then I do have two vectors. I have x fx1, fxn. gx0, gxn. Okay, so if I sample 4 points, I will have a 4-dimensional vector. Do you know how to take the dot product? Of course, I know how to do it. Okay, if I have 10 sample points, I have the 10-dimensional vector. Do you know how to do the dot product? Of course, you know how to do it. Okay, so let's do it for n, and eventually we'll let n goes to infinity. That will be how we measure the similarities between two functions. Okay. So what is, let's call it fn and gn. What is the dot product between fn and gn? That's just going to be sum. I am from 1 to n. fx0 dot gx0. Not x0, xi dot gxi. Moreover, because of the notation, we go from 0 to this. Okay, you take 3 points, you have a correlation. You take 30 points, you have another correlation. Our job is let n goes to infinity. You take infinite many points, you have the final correlation between two functions. Good so far? All right. Now, is this one well-defined? Number one, certainly not. Can you see why? The more points you take, the bigger the correlation, because you simply have more terms. Make sense so far? So number one, you cannot just simply take this. You have to normalize a little bit to make sure that, okay, if I take 10 points, I have a better correlation because I have a better correlation, not because I have more points. So I have more terms. Okay. So you somehow need to divide by 1 over n. Moreover, you need to consider the density of the points. So technically, what you should times should be b minus a divided by n. This part is called normalizing the vector. Otherwise, the longer the vector, the bigger the correlation, which certainly is not what we want. Sounds good? Okay. Now, what's this? If you let n goes to infinity. Does it look familiar? Zero. Oh. Does it look familiar? If not, change this to delta x, which is basically how you calculate b minus a divided by n.
Looks like an integral.
It's exactly the integral. Beautiful. From a to b. So this is how we are going to tell the differences between, or similarities between two functions. Now remember, you have infinite dimension because now you don't have a vector. This vector has all the values between a and b. It's infinite, but we can define this to be a new dot product, fg, which is defined to be this, this, this. Moreover, we want to put a bar here because we want to consider complex numbers. Okay, so that's the only difference we need to have, because everything we did before was based on real. We put a bar here simply because we need a complex number. Okay, where bar means the complex conjugate. A plus bi, if you take a bar, it's basically a minus bi. That's the complex conjugate. Okay. The reason we want that is because we want the z dot z bar is going to be the absolute value of z, which is the magnitude. No square root. So we want when f dot f itself, it should give you the magnitude of f squared. So this one basically looks like a vector now. You have a dot product, you know the magnitude of the vector. Sounds good? Okay, so number one, we extended the inner product for functions, which is in an infinite dimension vector space. Second, now let's consider all the periodic function. On the interval negative pi. Later, we'll extend this one to any interval and eventually to negative infinity to infinity. Okay, but for now, negative pi to pi. Why do we care about that? Because all signals in real life are periodic. Okay. You receive light from the sun. It's periodic. It's a wave. Okay. It's a combination of a lot of waves. If you listen to a sound comes in, it's a combination of a lot of sine and cosine waves. Okay, so any signals you receive from the real life has some pattern in it. And as long as you have pattern in it, you repeat yourself. As long as you repeat yourself, you are periodic. Good so far? So any signals you receive from the real world, the nature, is periodic. If it's periodic, okay, you can see this is negative pi to pi. You certainly have a period. It can be this. It can be that. It can be this. Okay. Then we start to wonder, we actually have a lot of signals with different frequencies. We have sine x, we have sine 2x, we have sine 3x, we have sine 4x, dot, 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 dot. We have all these kind of different signals. Okay. Now let's take a simple correlation test between them. What is the integration from negative pi to pi? Sine nx times sine mx dx. Okay. Because we want to see if I actually have a signal, I interfere it with a different signal, do they stay separate or do they start to actually have correlations? They start to interfere with each other. Okay, so I'm trying to compare the similarities between them. And what do we find? This is the product of sum formula. You have seen this before. The detail is really not important. Okay, it's going to be cosine, cosine. Basically, it comes from cosine n plus mx. It's going to be cosine nx, cosine mx, minus sine nx, sine mx, which is what we want here. Okay, so that comes from that formula. The detail is really not important. Okay, now can you do the integration of that? Well, that's going to be sine n plus m x minus sine n minus m x plug in pi and negative pi modified by a constant. Okay, so what do we have here? We need to plug in pi and plug in negative pi, right? So what do you have? For example, if you have 3 plus 2x, you plug in pi, what do you get? You got an integer multiple of pi, which gives you 0. If you got 3 minus 2, both are integer times x, you plug in pi, doesn't really matter, it's an integer. As long as it's integer times a pi or negative pi, it's 0. So can you see that? This whole thing here equals 0, as long as n does not equals m. Okay, that means if you take the integration from negative pi to pi, sine 3x and sine 5x, 3 does not equal to 5, so it's 0. If you take a 4 here, if you take a 6 here, 4 and 6 are not the same, it's 0. Good so far? That means if you take waves of different frequency, they do not interfere with each other at all. Unless you're actually having a signal, a wave, and another wave interacting with each other, and they have exactly the same frequency. As long as their frequencies are different, they don't interfere. Sounds good? Okay, that is basically what we can have. So what happens if n equals m? Then we have sine nx, sine nx again. Okay, once we have that, we can actually easily do it. It's going to be sine square. Okay, 1/2 1 minus cosine 2x dx, which is 1/2 x pi, negative pi, minus 1/2 sine 2x times another 1/2, so 1/4 pi and negative pi. So together we have 2 pi times 1/2, which is pi. Okay, and the minus 0, which is pi. And then we can say we only have 2 answers. We either have pi or we have 0. That's the basic fact we have so far through computation. All right, now think about what's going to happen. Why is this useful? Here comes the interesting thing. If you have a function which is periodic, okay, it's going to be, for example, 1/3 sine x plus 4 sine 5x minus 6 sine 7x. Okay. Now what you're going to do is you are going to actually probe this function with different waves with different frequencies. Good so far? You can probe it with sine x. You can probe it with sine 2x, 3x, 4x. You can try all the possible ones. Okay? What's going to happen? Number one, this one will have no response. If you probe it with sine x, sine 2x, sine 3x, sine 6x, it will have 0 response. Good so far? But it will respond to this frequency, and this frequency. Why? Because if you do the integration of that, you will have a number which is pi, just for this part. Make sense so far? Okay. Now imagine you don't know the formula of f. You just probe it. You can always do this, right? Through integration. And what's going to happen? You are going to receive a response. Sometimes you receive 0 response. Sometimes you receive a non-zero response. Good so far? For the ones you receive non-zero response, then you know. Even though I don't know the formula of ft, I know ft must have that corresponding sound wave inside. Otherwise, I should have a 0 response. Does that make sense here? Okay. That is super useful. Okay, think about it. What's going to happen? Think about when you try to talk to other people through the phone, right? What does the phone capture? The phone captures the sound of the bird, the sound of the environment, the sound of you, the sound of human, the sound of whatever. Good so far? They all merge together into one signal and got sent through the phone to the other guy. The guy received a signal, but the signal is already mixed. It's not like a clean 4 signal composed together. It's just one messy signal with a lot of noise inside. Good so far? Now what the receiver can do is actually the receiver can start to send waves to the sound they just received. They send a wave with the frequency of the bird. They receive a response. That means what? That means the original signal contains the sound of the bird. They send a signal of a train. No response. That means what? The original thing does not have a train sound inside. Good so far? So by doing things like this, by probing the signals with multiple different kind of frequencies, you can actually extract the frequency you want contained in the original signal. You can actually know how the original signal was formed before they were mixed together. It's almost like a decomposition. Actually, it's not almost like, it's exactly the same as a decomposition of the signal. Sounds good? Okay, that's the beauty of this. Okay, so that means if you probe fx, oh, I use t or x. I probe fx with sine nx, you will have 2 possible outcomes. No response, which means 0 if you do the integral. Then, or you may have non-zero response. Okay, that basically tells you this fx contains this signal, and fx does not contain. Okay, is the idea so far clear? When I say probe, I basically means take this function and take the integration. Okay, and if you receive discrete signal, you just take the dot product. You don't even have to do anything, just take the dot product and normalize it. Now you can see your application pretty quickly. Share MATLAB. Okay, now this is what I'm going to do. I am going to take a signal. I just manually created a signal, okay, with a frequency 50, a frequency 120, and a frequency 14. I merge them together. Okay, now what I can do is I can run this. Oh, you cannot see my graph. Okay, I just stop sharing. I share my desktop. Let's see what I got. This is the signal I already got originally. I make up some signal, which is a composition of 3 signals together with different frequencies. I sampled 100 points from here, signal. I fit it into the thing just now. I let sine 1x, sine 2x, all the way up to sine 500x to probe the original signal. Good so far? I only receive response at 13, 50, and 120. Okay, so I don't know the original signal, but once I do this kind of decomposition, I now know the original signal contains 3 things. That's beautiful. Okay, an immediate application is in real life, you never receive nice signals like this. Usually what you receive is a signal with noise, some random noise. Okay, so let's do this one again. Make sure I close everything, okay. Okay, this will be the random signal I receive. So it will be the composition of 3 signals plus some random noise, maybe you received from other of the sound in the environment or something like that. Now, if you do the decomposition, now what do you see? Number 1, you do receive a response for all kinds of different frequencies because you have not a lot of noises. Okay. Number 2, you still know the majority is going to be here, here, here. Moreover, you know the magnitude of these 3 things. It will not be as clean, as nice as before, but still you got the 3 major part. Good so far? Now what you can do is you can delete anything that is small, leaving only these 3. And then put these 3 back and merge them into the original signal. Still okay? Through this process, you take a signal with noise, erase all the noise, put the signal back, you just did a noise filtering. Okay, so that's how people do noise cancellation. The red one is the one after you delete all the noises, where the blue one is actually the original signal you receive, which contains a lot of noise, for example, from the channel, from the environment, which are the sounds that you don't want, which are the colors you don't want. Does that make sense here? Okay, so that's the power of the decomposition we just did. So basically now we have the tool to see any signal, to decompose it into whatever sine curve you have, and I will know how much component of sine 120x is inside, and I know all the detailed decompositions of different frequencies inside the original signal. That is the idea of Fourier analysis. Okay. And the thing is quite easy. You just probe it with different frequency. If that thing responds, that thing has one. If that thing doesn't respond, you just say, well, that thing doesn't have the frequency. And because we can do everything so quickly, you can actually just test every single frequencies all the way up to 5,000 within 1 second. And you have the nice graph like that. Okay. All right. So now if you think about what we just did, okay, we basically take a signal from negative pi to pi. We basically just probe it with sine nx. Okay, by taking the integration, and then we just check, okay, do we receive a response or not? We may receive 0, we may receive the amplitude of the original strength of the signal of that frequency. Now go deeper. What did you just do? Basically what you did is actually you decomposed the original signal into A1 sine x plus A2 sine 2x plus A3 sine 3x plus A4 sine 4x dot, 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 dot. What you did is you write the original thing into a linear combination of all the possible sine curves you have with different frequencies. That's what you did. Okay. What's going to happen? You are going to receive a 0. if your original signal does not have this component. And you will receive the amplitude you want if nothing does have the frequency you want. Sounds good? Okay, so basically you're rewriting the original thing into a linear combination. Now, if you go back and look at this again, it becomes super interesting. Why? How do you get all these things? Well, you got all these things from this thing. That's basically what you mean by your response. That's what you mean by what you take from the original, signal. But what is this? This is nothing but sine nx and sine mx. This is nothing but the dot product between two functions. So now let's rewrite everything we had before. Exactly the same, but in the dot product notation. Does it remind you of anything? You have a lot of vectors. Okay, the dot product with each other is going to be 0, except when they dot product with themselves, you got something non-zero. Do you remember what do you mean by dot product equal 0? Orthogonal, right? Now you have a set of functions, let's call them vectors, a set of function vectors, okay? They're orthogonal to each other. Okay. What do you have? Then they form an orthogonal set. And if you have enough of them, they form an orthogonal basis of the whole periodic function. Then any periodic function will be able to written as a linear combination of this orthogonal basis. Moreover, the coefficient before the orthogonal basis is super easy to compute because you just need to take the dot product of the original vector and the basis because they're clean. They're all orthogonal to each other. Sounds good? Okay, so that's the idea here. Of course, we need to clean things up a little bit. For orthogonal basis, we want this to be 1. Okay, but we have pi. That's easy to change. Let's just change them to be 1 over square root of pi. Before, if you take the integration, you got pi. Now, if you take the integration of this, of course, you will have 1. Then sine nx n from 1, 2, 3, all the way to infinity. Just there. Now we need to add in something more. We also need all the cosine nx for periodic. The reason is because sine x, they always have 0 on the two ending points, but you may have some wave which start from non-zero, so you need some of the cosine. And then you need to add one more, that is a constant, okay, which is basically 1. They together forms an orthogonal basis of all periodic functions. Defined on negative pi to pi. Okay, which means any periodic function can be written as a0 plus a1 sine x plus a2 sine 2x dot 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 plus b1 cosine x plus b2 cosine 2x and dot 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 can be written as a linear combination of all of them. Okay, so let's use I or n. Let's use n. an sine nx plus sum n from 1 to infinity bn cosine nx. That is called Fourier series. Of fx. You take a signal, you decompose into the summation of all different signals. Each one has a integer multiple of the frequency. Moreover, you do know how to compute each constant. Okay, an is nothing but where is it? Ft sine nx divided by pi, okay, which is integral from negative pi to pi Bn is the same 1 over pi cosine nx, which is 1 over pi, negative pi over pi, fx cosine nx. Okay. If this is not 0, that means an is not 0. If an is not 0, that means you have the component sine nx inside, just as the prob idea we just did before. Okay, so you can imagine what I just did with the signals. Basically, I was trying to see, okay, what are the coefficients for sine x, sine 2x, sine 3x, sine 4x? I found only sine 13x, sine 120x, and sine 40x responded. All the other coefficients will be 0. Therefore, I'm pretty confident that the original signal only contains these 3 frequencies. And moreover, I have the magnitude of them. Okay, you can do things in this way because they are orthogonal to each other. If they are not orthogonal to each other, it's going to be difficult to get the coefficients before them. A little bit more difficult, not too much difficult. Okay, but since it's already orthogonal, it's pretty easy. Just take the dot product and do the projection. Sounds good? That's very serious. Now we want to extend the idea. We want to keep going. Before, that thing only works from negative pi to pi. Now we want to make sure that thing works on any kind of thing. Any kind of interval can be longer than pi. Okay, can start from anywhere. It doesn't have to be orthogonal, symmetric. So we'll just take anything with L. This L can be long, can be short. It doesn't have to be 2 pi. We have the corresponding thing. So let me write it down. For any L periodic function, not 2 pi periodic, but L periodic, all you need to do is just repeat what we had, except you stretch everything. Okay? So you can still do it. Now I'm going to use the standard notation, A0 divided by 2. Still an sine. Before you have sine nx. Okay. Now you have sine 2 pi nx divided by L. Bn cosine x. Before you have nx, that works for 2 pi. Now you want something with L, you just do 2 pi nx divided by L. Okay. Of course, your AN and the BN is going to change a little bit, but not too much. AN is going to be 2 over L integration on L fx sine 2 pi nx over L. Bn 2 over L fx cosine 2 pi nx over L. Okay, so far we can do any intervals, not just negative pi to pi. It can be longer. Now next, what we want to do is we want to write these two things together. You have cosine, you have sine. How about we just write it in terms of E, because E contains both cosine and sine. In this way, not only we can handle plane waves, we can handle complex waves. So extend to complex. I will skip the details. But basically what you have is a ck e to the ikx. This time you have cosine and sine both contained in here. Okay. Some variations, it doesn't really matter that much. When you write it down, you will see they're the same. Okay. Here k has something to do with your L and 2 pi. Finally, before we talk about the frequencies, right? You have sine x, sine 2x. Sine 3x. What you notice is they're all integers. You cannot have sine 1.2x. You simply just don't have that option. So that's why we only have the frequencies with integer multiples. Even if you change the size, you still have 2n pi over L. This n here tells you that the smallest thing you have is 2 pi over L. It's just 2 pi over L times 1 or times 2 or times 3 or times 4. So it's still discrete. Good so far? Now I want to do it again. We want to take something discrete. We want to say, what if we can actually handle every single frequency, not just the integer multiples of the minimum frequencies? The math is pretty long. So I will just write down the conclusion, but I think you can see the connection. Extend to continuous case. Then of course, sum become integral. Okay. C is now a function of x, because for different k, but your k is very, very different. Negative ei omega t d omega. So I don't want to call it c, I want to call it omega. That should equals to your ft. So before your k can be 1, 2, 3, 4, 5, 6. Now your k can be anything. Your k can be 0.1, 0.3, but you cannot take the sum anymore, take the integration. Okay, but the formula looks exactly the same. So this CW, I'm actually going to notate it to be F hat W. You can simply do the computation. It's going to be this. Ft e to the negative I omega t with a 1 over 2 pi. All right. So this is called the Fourier transform of ft. It is given by this formula, 1 over 2 pi. So if you know a function, you can know the Fourier transform of that function by plugging in and doing the integral. When you finish, you will receive a W, omega, which is basically the frequency. And then this is going to be the inverse transform. Let me see, how do I want to use that notation? Okay. Inverse Fourier transform of f omega is going to be ft equals ei omega t d omega. So the only difference is this one has a negative, this one does not have a negative. It comes from the idea of the conjugate. Okay. My signal is the sum of all possible signals times the corresponding coefficient. The coefficient is 0 if my signal does not have that signal. Okay. The coefficient is going to be high if my signal contains a lot of that frequency. And I check it with every single possible frequency from negative infinity to infinity. Moreover, the coefficient of each frequency is computed by my Fourier transform. Okay, so that's the whole idea of Fourier transform. This is in the frequency domain. Let me write down this. Time domain, t, and the frequency domain, omega. Sometimes it's easier to do things in t. Sometimes it's easier to do things in omega. And we have the freedom to go in and out, whichever way we want. Sounds good? Okay. This is the Laplace transform. Oh, wrong place. This is the Laplace transform. This is the Fourier. Do you see the similarity? Okay, so think about, how did we get Fourier analysis again? We were trying to compare how similar our original signal is to a certain sine cosine wave, which is captured by e to the iwt. Good so far? Then for Laplace transform, what are you trying to do? You are trying to compare how similar your function is to exponential. Not to sine cosine anymore, to exponential. Okay, so what's the most complete analysis? It should be these two combined together, because you can notice this one only have imaginary, this one only have real. When you put the real and the imaginary together, it's going to be the most general case, which looks like this, but your S can be complex. Okay, so Laplace basically handled this A part, and Fourier analysis handled this BI part. They put together, you have a very complete analysis that includes exponential for the real, sine cosine for the complex. Okay, so there's a bigger picture between this. Sounds good? Okay, go back, try to Google something, and I don't know if there's any gap in the instructions I just did. If you have questions, bring it tomorrow. Okay, this thing has, Fourier analysis is probably one of the most important thing you need to know, no matter you're going into engineers or mathematics. Okay, and you can already see that it's very, very, very useful. Okay, that's all for today.